Now we'll continue one important concept in relation. The concept is basically equivalence classes and partition. So previously we have done the concept of relation, especially the equivalence relation. Based on this concept, we'll first do some theory and then we'll continue the problem related to equivalence classes and partition. So what exactly are defined by a class or equivalence class? So our first definition is here. Let rho be an equivalence relation and equivalence relation, that means the relation is reflexive, symmetric and transitive, on a set S and A belongs to S. So this is basically a set and we have taken one element A from the set S. Then the class of A, you can say the equivalence class. Then the class of A is denoted by class A, CLA, and is defined by class A. It is basically a set which contains all those element X belongs to S such that X is related to A. So here class of A basically like this. It contains all those element X which is related to A. So sometimes you will see, that is important note, the class of A, CLA, or some people have written is box A. This also represent class A or A bar. So all are basically represent the class A, but before that you need to think about the relation rho must be an equivalence relation. Otherwise we can't form any kind of class. So this is basically all those elements of the set is such that B is related to A. Or you can say A is related to B, no problem. So there is another important note that you will observe. This is note 2. If A is not related to B, that implies class of A intersection class of B. This is basically phi. That means they are completely disjoint if A and B are not related. So here is B. A and B is not related. So on that case, the class of B, that set is basically class of B. And that is class of A. It is completely disjoint. Whereas, if A is related to B, that implies that this class are identical. Class A and class B will be same. So here I am using that symbol is for related, and that symbol is basically not related. And the third is, if B belongs to class of A, that implies B is related to A. Okay? And this is if and only if. So now we'll come to some theory. The first important theorem is here. This theorem is important in the graduation examination for the graduate course. What is the theory? The theory is basically saying that let rho be an equivalence relation on a set capital S and A comma B belongs to S. then class of A equals to class of B, that implies A is related to B and converse is also true. So this is if and only if. So we will prove this theorem. How we will prove? So what is exactly given? It is given rho is an equivalence relation on S. This is given. So what we will prove? First we assume that class A equals to class B. Let class A, we prove that side. Class A equals to class B. And from this we can prove A is related to B. So how will prove? How will prove that side? From if we consider class A equals to class B, that means A is related to B. So let this one, this is basically say 1. Let we are considering X is related to A. Take arbitrary element or X is related to A. So what exactly mean by this? This means X belongs to class of A. And since class A equals to class B, so that implies X belongs to class of B. Why? By 1, what we have? We have class A equals to class of B. So if X belongs to class B, so that means X is related to B also. So what we get now? So here we have X is related to A. That implies X is related to B. X is related to B. And from this we can write A is related to X and X is related to B. Why? Because of symmetry. Since rho is an equivalence relation on S. So A rho X, that implies X rho A. Symmetry holds. And since A rho X, X rho A, again rho is an equivalence relation. An equivalence relation on S, that is basically that holds the transitivity holds. So therefore transitivity holds. So what exactly we know? A is related to X and X is related to B. That means A is related to B. So what we proved? We proved here class A equals to class B. That implies A is related to B. Now we'll prove the converse part. We'll consider A related to B. From that we'll prove class A equals to class B. So now we'll prove that side. We consider let A is related to B. And from this we will prove class of A equals to class of B. But the question is how to prove. So you just consider the recall. The recall is when two set will be equal, A equals to B. So first you will show A subset of B. Next you will show B subset of A. And from these two conditions, you must prove A is equals to B. So here you just consider A is your class A and B is the set class B. So how will show? First we will show class A subset of class B and class B. So what we will show? We will show class A is subset of class B. This will be 1. 1 we have used before, I think. So this will be 2. And after that, we will prove class B is also subset of class A. This will be 3. So therefore from 2 and 3, what we conclude? We conclude that class A equals to class B. So this is our construction. How to prove? So now we'll show class A subset of class B. So what we'll take? So we take one element, let X belongs to class A. So A is subset of B. So X belongs to, if X belongs to A implies X belongs to B. That means A subset of B. Take any arbitrary X. X belongs to class A. What exactly it implies? Then X is related to A. Now A is related to B. It is given. So now X is related to A and A is related to B. So this is by star. So if you use the rho is an equivalence relation, we use the transitivity rule. So X related to B because of by transitivity. Transitivity, as rho is an equivalence relation. Equivalence relation. So X is related to A is related to B. That implies X is related to B. So that implies X belongs to class B. So what we proved? Class A subset of class B. Why? Since X belongs to class A, this is basically arbitrary. Okay. Now we'll come to the class B subset of class A. How we'll prove? We'll consider, let say Y belongs to class B. And we'll show here Y belongs to class A. From that we can prove class B subset of class A, since Y belongs to in similar way is arbitrary. So what exactly mean Y is related to B? So now Y is related to B and A is also related to B. That is from star. So that means Y related to B and we can write B related to A. Why? Because of bisymmetry. Bisymmetry. And that implies Y is related to A by transitivity, as rho is an equivalence relation. Y is related to A, that means Y belongs to class A. So if Y is arbitrary, so class B is subset of class A. So from 2 and 3 we conclude that class A equals to class B. So what we proved? We proved here if A is related to B, that implies class A equals to class B. That means these two classes are identical. So where we have proved the theorem, if rho is an equivalence relation on a set S and AB belongs to S, then class A equals to class B if and only if A is related to B. Now we will prove the next important theorem. This is theorem 2, and that theorem is very, very important. What is the theorem? Let rho be an equivalence relation on a set capital S and A comma B belongs to S. Now then, if A is not related to B, it implies if A is not related to B, then what we proved? Class A intersection class B, this is phi. They are basically disjoint. So how will prove they are basically disjoint? Proof what is exactly given? So the given information is rho is an equivalence relation on the set S and A comma B belongs to capital S. And also it is given A is not related to B. So what we have to prove? We have to prove that these two class A and class B, this is basically disjoint. That we have to prove. So here we assume that if possible let they are not disjoint. So that means they are non-empty. So that means X belongs to class A intersection class B. Now we will just apply the definition of intersection. So then X belongs to class A and X also belongs to class B. Just X belongs to intersection B. That means X belongs to both A and B. Okay. So this is class A and this is class B. Here we have taken X. Class B. So X belongs to class A, that implies X related to A according to the definition of class. And X belongs to class B, that means X is related to B. So now we can write X is related to A as A related to X. X is related to X row A, that implies A row X because of symmetry. And X row B. So here we apply by symmetry relation. Symmetry, as row is an equivalence, so symmetry must hold. Now A is related to X, X is related to that implies A is related to B. This is by transitivity. Transitivity. But which is a contradiction? This is a contradiction. Which is a contradiction. Why contradiction? Because it is given A is not related, as it is given that A is not related to B. But we get here A is related to B. What is given is not related to B. So it contradicts each other. So why the contradiction appears here? Because we have taken one element from both class A and class B. So that means this assumption is basically wrong. So what is true? Class A intersection class B equals to 5. So therefore, class A intersection class B, this is basically 5 if A is not related to B. Okay. So this theorem is proved. So now what we conclude? What is our conclusion? Our conclusion is, let rho be an equivalence relation. Equivalence relation on a non-empty set capital S and A comma B are two element in S, then class A and class B are either disjoint when it will be disjoint when is not related to B, or identical when it will be identical when is related to B. Okay. So thank you so much.